Hello mathematicians, we're now going to have a look at the definite integral with particular regard to its properties. So the things about the definite integral are probably things which we would have assumed anyhow. The values of the definite integral can be combined. So if we took the integral from c to a of f of x, for example, then we could break that up into two separate integrals, as the integral from a to b and then the integral from b to c. That's illustrated below, where if we look at the integral from minus 5 to minus 4 of our curve, we're going to get this value here for the area under the curve. So whatever the function is, when we apply the fundamental theorem of calculus, find the primitive, again whatever it is, and plug these into it, we get this. And then the integral from there to there is 1.57, and if we did it in one jump, took the integral from minus 5 to minus 3, it gives us 2.63. Now that's almost self-evident, but we need to make sure that we can justify making that sort of jump. If we look at a curve which cuts through the x-axis, then it's really important for us to realise that the values of the definite integral are positive for areas between the curve and the axis that are above the curve, and negative for areas below the curve. So down below here, we can see that we've got this brown area here, which is the area above the curve. It's plus 3.07. The green area is minus 3.74. If I take the integral from minus 5 to 0, so I just add the two integrals together, they actually add as directed numbers. So 3.07 plus minus 3.74 to give us a total of minus 0.67. Now that will be important later on, because if the question just says, do this, take the integral, then we're not worried about whether it goes above or below the curve. That will all get taken care of by our substitution. But if the question actually asked, what is the magnitude of the area trapped between the curve and the axis, we would have to know that we're cutting the axis, and then for this green area down here, we would have to take the absolute value of that integral, so that we could add the two together to get a total area of, what's that, 6.81. So there's a distinction between area, which is just the amount of two-dimensional space, if you like, trapped between the curve and the axis, and the value of the integral that we'll have to be very aware of. So let's have a look at GeoGebra just to explore this a bit further. So we can look at this one curve here. We can see at the moment that the integral from minus 5 to wherever that is, minus 2.8, has a total value of 2.84, and it doesn't matter where I break the shape up. So if I shift this, then the two sections are two separate integrals, but if you notice that the total is always 2.84. Now, while we've got this up, we could then also have a look at the positive and negative aspect of this curve. So if I take this beyond here, if you look at the area of the green part of the curve, it's 2 just there, but when I keep going to the right, it all of a sudden starts to drop. And that's because the area below the axis is negative. So it's like I'm cancelling the two areas out because they're directed numbers. So just a tiny little point, but when I get to that spot there, what that's telling me is that the area above the curve and below the curve, from minus 4 to, what's that, negative 0.72, are equal to each other. So that we have to take account of when we've got positive and when we've got negative areas. And we can just play with this thing here. If we were after, again, the total area trapped between the curve and the axis, we would have to break this up into two integrals, the brown one and then the green one, and take the absolute value of the green one. Now the next point we're going to have a look at concerns symmetry. So if we have an odd function which has pointwise symmetry, as we know, so if we take this function here, which has pointwise symmetry, then what we can see is that if we take the integral from minus a to a, so from points equidistant either side of the axis, then we've got a positive area over here, a negative area here, and they're going to be, because of symmetry, equal in magnitude to each other. So if we just take one integral from minus a to a, we're going to get an answer of 0. But if it was the area under the curve that we wanted, we would have to take twice the integral from 0 to a of the odd function. Or I suppose you could say twice this integral, but make sure you took the absolute value of that. So we'll have a look at that on GeoGebra, and while we're there we'll have a look at the even function as well. And what we can see with the even function is that because again of symmetry, if we go the integral from minus a to a of an even function, that's actually twice the value of the integral from 0 to a or from minus a to 0 of the even function. So let's go to GeoGebra. Very quickly, for our odd function, we can see that to the left we're going to have negative areas, to the right we've got positive areas, but when we go from points which are symmetrical either side of the origin where we have pointwise symmetry, so I'll move this one to 1.5, then in that case we're going to get a total area of 0. So if I wanted a total integral of 0, if I wanted the total area, I would have to take the green one and double it. Likewise, for an even function, the area under each side, for want of a better word, of our even function is symmetrical, so the total area is just twice the area under one side if we go from equal distances. So if I made this 1.5, for example, and made this 1.5, then either the brown or the green area are 1.13. The total area is double that, at 2.25. And that's just a rounding error on GeoGebra. While we're on GeoGebra, we will just have a look at a couple of the other properties and then go back to our notes. So this particular property is about the sum of definite integrals. So here I'm going to say that we've got this curve, so it's x squared, and I'm going to integrate it from minus 2, let's go from minus 2 to, well, go 2. So the result of that integral is 4.98. If I introduce another term, which is x, then the integral under x from minus 2 to 2 is 0, because we've got an equal positive area and an equal negative area under that. So just switch that one off, you can see that. So they cancel each other out when we do the integral. And if I look at hx, where it's 1, then the integral from minus 2 to 2 of 1 is 4 units, as we can see from geometry. Now if I add all of those together, so I'm looking at doing the integral from minus 2 to 2 of x squared plus x plus 1, then I'm hoping that I'll get 9.33 as the result of the integral, which we do. So what that shows is what we've already assumed, basically, that if I have the integral of a sum, I can break that sum, or difference, up into separate integrals. So the integral of a sum is the same as the sum of the integrals. And the integral of a multiple is the multiple of the integrals. So if we look at our integral here, f of x, where that's x squared, and I multiply that by a constant, in this case the value of 2 up here, then the area under the curve 2x squared is 6, which is of course twice the area under the curve x squared. And that holds for other values of k as well, clearly. K is 3, k is 12, down to negatives as well. So this is interesting, that we can multiply by a negative constant. The absolute value of our integral is going to be the product of the constant times the area under the curve. So back to our notes. The integral of a sum equals the sum of the integrals we've encountered. So we can just break an integral up into separate terms. Doesn't matter whether this is a plus or a minus between them. The integral of a constant times a function is the constant times the integral. So we can do the integral with the k still in there, or we can actually take it through the integral sign and write it like that. This one up here is also important, that if we take the integral from a to b of f of x dx, that's actually equal to minus the integral from b to a of f of x dx. Now that's not quite so obvious geometrically, but it's an important point. So we generally go from the smallest value of x to the biggest value of x, and that avoids us having problems of unintended negatives. So have a go at these questions in 11C and try and get your head around the properties of the definite integral.